Hello, I'm Lan Pye and welcome to my kitchen. Also, welcome to our talk. This is Container Level Network Observability with eBPF. I'm presenting joint work with Will Glauser, and we're both at Kentik. Let's jump right in. So, container networking, why should I care? Well, you have a container, you have an application running in a bunch of containers, and people are telling you it's not working. Is it that network? Is it the application? How can you quickly identify what the problem is? If you inspect the state counters, look at TCP problems, you can see are the bytes going as they should? And if they are, you can dig in. And if they're not, you can look at the application. Another common use case is top talkers. Network is a finite resource. You have 1,000 containers, and you want to quickly identify which one of these 1,000 containers is taking up all of the bandwidth and sending all the packets. Lastly, we have a security use case. You have 1,000 containers, and they're all talking to various endpoints. You want to have a whitelist and a blacklist, and really observe exactly who everyone's talking to, sort of a firewall case. So why is this hard? Well, let's take a look at a typical Docker setup. This is an image I found online, and it sort of illustrates the problem. So what we have here is two containers. They want to talk to each other. They want to talk to applications running on the host OS, and they want to talk to applications in the external network. By my count, we have 4 interfaces, and in a traditional world, you'd want to monitor all 4. This is really the point of this talk, is that when it comes to network monitoring, you don't want to think about the network, you want to think about the kernel. Monitor kernel state, let the kernel tell you about the network. And jumping right in, what are some alternatives? Well, we have PCAP. PCAP would give you the data you need with the expense of high CPU and having to send every packet out of kernel space into user space and just look at the headers and toss it all out. You still have the dynamic interface problem where it's working on a per interface level, not on the kernel level. Service mesh would get you what you need, but it would be extremely complex to set up. And you also have the problem of moving local traffic into non-local network all of a sudden. And lastly, we have eBPF. The kernel knows all about the bytes and packets coming in. We can just ask it to report things periodically. So how does this all work? As a demonstration here, we have an open source tool called Convis, Container Visualization. This is available on GitHub at kentik/convis. And here's a quick example output. Takes no flags, takes no arguments. You simply run it as root, and it starts spitting out exactly what TCP connections are going on. I have a simple container, which is running wget, and you can see it's recording the connection and the close events here. Also, we have Chrome snuck in a close event as well. And so you can see how it's really recording everything on the host, not just a specific interface or container. How does it work? So take a look at bytecode.c, and you can see that we're instrumenting 4 calls, really. So these are basically around setting up a TCP connection, accepting a TCP handshake, and running a TCP close. Diving in further, we have, if you look at it, the magic here is really happening on line 157. So when you instrument TCP close, you get a struct sock, and that contains that's basically a pointer right to everything that the kernel knows about that connection. And then we simply turn it into one of our custom events. We have source address, dest address, sort support, dest port, remember N to H, that's network byte order. And we just sort of sticking in our custom event ID, and protocol is 6 because it's always going to be TCP. Lastly, we simply tell it to go right back out to our reporter with our event output. Jumping back up a little bit, let's look at the Rust level. Rust has made a lot of strides here lately. There's a IA crate and also a Docker crate that we're really leveraging very highly. This is the main event loop right here. And what we're basically doing is we simply load up the code, make sure it looks good. We load up a Docker crate to tell us about all the containers on the system. And then at line 42, we call code.exec. We simply wait for events to come back and print them out. Code.exec is leveraging the IA again. We simply connect the probes and send them in with really just very straightforward kprobe.attach. And then here's the where we receive the events from the kernel, and then we pass them back to that main loop again. Once again, it's Lan Pye, and I've been presenting work with Will Glauser, and this is all available at github.com/Kentik Convis. Thank you for your time.